Hello. In this video, I intend to study series in a normed vector space. I have chosen the following exercise as a basis for discussion. Show that the following matrix series is convergent and calculate its sum. It is the matrix series sigma from n equals 0 to infinity of the 2x2 square matrix 1/3 minus 1/3 2/9 minus 4/9 to the power of n. Thus, as we can see, it is certainly a series in the normed vector space of 2k2 square matrices with real coefficients. We are faced here with the complex problem of calculating the challenging powers of a matrix. We know that this kind of successive power calculation of a matrix is simple in certain cases, particularly when it is a diagonal matrix or a nilpotent matrix, because we know that from a certain point the powers will cancel out. It is therefore legitimate here to ask the following question. Is the matrix that appears in the series a diagonalizable matrix? Let's call it A. So let A be this matrix. To see this, we will calculate its characteristic polynomial. This polynomial is given by P of x equals x2 minus the trace of A, x, plus the determinant of A. We do not need to use the general form determinant of Ailey here, since we know that the coefficients of the characteristic polynomial are minus times the trace of A, and the constant term is equal to the determinant of A. This gives us equal to x2, so the trace is 1/3 minus 4/9 times x plus the determinant, thus 1/3 times minus 4/9 minus 2/9 times minus 1/3, which gives us, after all calculations, x2 plus 1/9, x minus 2 over 27. The eigenvalues are therefore the solutions of the equation P of x equals 0, and we find its distinct eigenvalue problem lambda equals 2/9 and mu equals minus 1/3. Since these two eigenvalues are distinct, this is enough to assert that the matrix is diagonalizable. It is a square matrix of order 2, and thus there exists an invertible matrix P such that A can be expressed in the form A equals P times D times the inverse of P, where D is the diagonal matrix with diagonal terms 2/9 and minus 1/3, that is, the eigenvalues. We are therefore looking for the nth powers of A. At this point, we can write that the partial sum of our matrix series is written as Sn equals the sum from k equals 0 to n of 1/3 minus 1/3 of 9/9 minus 4/9 to the power of k. It is therefore the sum from k equals 0 to n of a to the power of k, and by replacing a with the expression from earlier, it is the sum from k equals 0 to n of p times d times the inverse of p all to the power of k. So we know that in this product the p's simplify with the p1s, and sen takes the form of the sum from k equals 0 to n of p d to the power of k, p1, inverse of p. By linearity, we can take out the p. And thus it becomes in the form of p times the sum from k equals 0 to n of d to the power of k, p minus 1, which can be written in the form of p times tn times p minus 1, where tn is the sum of the powers of d from k equals 0 to the powers km of d from k equals 0 to n. Tn obviously is therefore, since we can sum matrices term by term, Tn is thus the matrix with coefficients sigma from k equals 0 to n of 90 to the power of k 0, 0, and sigma from k equals 0 to n of negative 1/3 to the power of k. Here we find the partial sum of a geometric series with terms 29 to the power of k, which is the sum of a geometric sequence. We know that since 29 is less than negative, 1/3 in absolute value and strictly less than 1, these sums converge, these partial sums converge. The first will give us 1 over 1 minus 29, and the second will give us 1 over 1 minus 1/3, or 1 over 1 plus 1/3, which gives us as the limit of the partial sum Tn. The matrix 9, 7, 0, 0, 3/4. So what about the limit of our initial partial sum Sn? From the relationship between alpha r and d, we see that tin, or rather Sin, appears as the image of tin by the application on the normed vector space of 2×2 square matrices with real coefficients into itself, which associates to each matrix M the product P times M times P minus R. So Sn is the image of tin, seen as f of tin. This application is visibly linear with respect to dur M. Therefore, it is continuous because we are in finite dimension. It's easy to show a linear application in finite dimension reduces to a function of several variables whose components are first-degree polynomials and thus continuous. From the vector space to and if the components are continuous, the linear application is continuous. It's a very simple exercise. We thus deduce that the limit of Sn as it approaches infinity is the limit as it approaches infinity of f of Tn, which is none other than f of the limit by continuity of Tn, and thus it is f of the result 9, 7, 0, 0, 3, 4, which gives us p times the matrix 9, 7, 0, 0, 3, 4, p1. So all that remains to be done is to find p. We know that p is composed of eigenvectors. Thus, we need to find two eigenvectors that generate the eigenspaces associated with the eigenvalues lambda and mu. For lambda equal to 1/9, we can take as a vector v1 equal to 1, 1/3 transposed. The work is easy. You solve ax equals lambda x, and you find a simple system of two equations with two unknowns, and we can take 1, 1/3 as a vector that generates the eigenspace associated with lambda. Similarly, for mu equal to minus 1/3, we can take the vector v2 equal to 1, 2 transposed row vectors. P is therefore the matrix having as columns 1, 1/3, and 1, 2. P1 is 1 over the determinant of P, easy to find. We swap the 1 and the 2 in place and change the other terms accordingly. And finally, the limit of Sn as it approaches infinity is therefore 3/5 times P, 1, 1/3, 1, 2 times the limit of Tn, 9, 7, 0, 0, 3, 4 times P1. Finally, 1 over the determinant is already there. 2 minus 1/3 minus 1, 1, and we find 39 over 28 minus 9 over 28, 3 over 14, and 9 over 14. In this tutorial, here is a comprehensive and detailed way to handle an exercise on matrix series with a step-by-step explanation of the process. Thank you.